talking about, well, the most mysterious things out there. Black holes. These things, they don't just swallow stuff up, they really make us question our basic understanding of reality. Physicists even call it the gravest of paradoxes. So, let's dive in. You've got these two huge pillars of physics, right? Einstein's general relativity, that's our picture of gravity, space-time on the big scale.
Right, the cosmic view.
And then there's quantum mechanics, our amazing theory for the tiny microscopic world.
Incredibly successful, yeah.
For a long time, they seemed fine, ruling their own domains, but what happens when they meet, especially around something as extreme as a black hole? Well, that clash creates this deep puzzle, this thing that's bugged physicists for, 50 years now, the black hole information paradox. So our mission today is to really get our heads around this. Why does it matter so much for, the fabric of the universe, and what crazy ideas have physicists come up with? We'll trace it from just a theoretical head-scratcher to maybe something like a resolution, and we've got our sources here to guide us through this deep dive.
And the stakes, well, they really couldn't be higher. This isn't just some abstract puzzle, It hits right at the heart of quantum mechanics, this principle called unitarity. Unitarity is basically the quantum guarantee that information, it's never truly lost or created, for that matter.
Right.
If that gets violated, if information can be destroyed in a black hole, then, well, our universe isn't predictable in the way we've always assumed. It messes with our ability to figure out the past or forecast the future. It's what physicists call a catastrophic loss of determinism.
Wow, that's, unsettling. So maybe walk us through how this whole conflict, this paradox, actually started.
Sure. It really begins with general relativity, Einstein's theory. It predicts that when a really massive star runs out of fuel, it collapses under its own gravity. Boom, black hole. And these things have two key features: a singularity at the center, super dense, and this event horizon.
The point of no return.
Exactly. Cross that line, and you're heading straight for the singularity. No way back.
And there's this thing about classical black holes, the no-hair theorem. That sounds weirdly simple.
It is, kind of. It just says once a black hole settles down, you only need three things to describe it from the outside.
Yeah.
Its mass, its electric charge, and how fast it's spinning its angular momentum.
That's it.
That's it. So it doesn't matter if it was a star or a gas cloud or, a giant pile of books that collapsed. From the outside, looks the same.
So all the details, the information about what it was, its hair, it just vanishes behind the horizon. You can't see it anymore.
Right. And in that purely classical view, before quantum mechanics really got involved, that wasn't seen as a paradox. The thinking was the black hole lasts forever. It's a permanent prison, sure, information's locked up, inaccessible, but it still exists in there somewhere. The real trouble starts when quantum mechanics steps onto the stage.
Okay, so general relativity locks information away. What does quantum mechanics, the other big theory, say about information?
Quantum mechanics is totally different. It's built on this absolute rule. Unitarity. Information has to be conserved. Quantum evolution, how things change over time, it has to be reversible. You can scramble information, make it super hard to read, but you can't fundamentally erase it. This means pure quantum states have to stay pure states as they evolve.
Can you clarify that a bit? Pure versus mixed states? Why is that so important here?
Think of it like a pure state is like having a perfectly sharp photograph. You have complete information about the system's quantum properties. Its entropy, specifically von Neumann entropy, which measures quantum fuzziness, is 0, perfectly defined. A mixed state, though, it's more like a blurry photo. There's some inherent uncertainty, some information missing or averaged out. It has positive entropy.
Okay.
And unitarity strictly forbids a pure state turning into a mixed state. If that happened, information is irreversibly lost. You couldn't, even in principle, rewind the universe's tape and get back the exact starting point, or predict the future perfectly.
Right. That definitely sets up a clash. But then, around 1974, Stephen Hawking came along and, dropped a bombshell, didn't he? He brought quantum theory to black holes.
He absolutely did. He discovered they aren't eternal. They leak. They emit what we now call Hawking radiation, and incredibly slowly, they evaporate.
How does that work again? Something about particles near the edge.
Yeah, it's quantum weirdness near the horizon. Virtual antiparticle pairs are constantly popping into existence. Usually they just annihilate each other. But near the horizon, sometimes one falls in carrying negative energy, which reduces the black hole's mass while the other escapes. That escaping particle is the Hawking radiation.
So the black hole just shrinks over time.
Over immense timescales, yes.
Yeah.
Eventually, it would disappear completely.
And this is where it gets really sticky, right? The nature of that radiation, Hawking found it was Thermal. Random.
Exactly. Perfectly thermal, like the glow from a hot piece of coal. It only carries information about the black hole's overall properties. Mass, charge, spin. Nothing about what fell in originally.
But hang on. If you start with a pure state, like our perfectly defined star, it collapses into a black hole. Then the black hole evaporates into this purely random thermal radiation, which is a mixed state.
Yep.
Then the original information of the star, it's just gone, erased. That smashes right into quantum mechanics, doesn't it?
That's it, precisely. All the unique quantum details that made up the star vanished, replaced by generic heat. It's an irreversible leap from pure to mixed. The past becomes unknowable, in principle. That's the catastrophic loss of determinism that just stunned everyone.
And then Don Page came along in the 90s and made it even clearer using this entropy idea.
Right. Page sharpened the paradox using von Neumann entropy. He basically asked, what should the entropy of the Hawking radiation look like if quantum mechanics holds true? In Hawking's original picture, the radiation's entropy just climbs steadily up as the black hole evaporates. It gets more and more entangled with the black hole interior, but then the black hole disappears, leaving only this highly mixed radiation entangled with nothing, which makes no sense physically.
So what did Page say should happen?
He said if evaporation is unitary, the radiation's entropy should initially rise, yes. But then, after roughly half the black hole's entropy has been radiated away the Page time, the entropy must start to decrease. It has to go back down to zero by the time the black hole is completely gone. This shape up, then down, that's the Page curve. It became the benchmark. Any real solution had to reproduce that curve.
And that just seemed impossible from a gravity perspective, didn't it? How could gravity calculations possibly show that downturn?
That was the huge puzzle. Hawking's calculation seemed solid, but it led to this impossible situation with entanglement. It was like the universe's books weren't balancing. Something fundamental was wrong.
This crisis really forced people to think outside the box. You mentioned a clue came from black hole thermodynamics, entropy being related to surface area, not volume.
Yeah, that was bizarre. Usually entropy scales with volume. But for black holes, it scales with the area of the event horizon.
Like the information is written on the surface.
Kind of. It's like, yeah, information isn't stored inside the room, but maybe on the wallpaper. This led Tuft and Susskind to this radical idea, the holographic principle.
Holographic, like those 3D images from a 2D film.
Exactly, that analogy. The principle suggests that maybe all the information needed to describe a volume of space can actually be encoded on its boundary, a surface with one less dimension. For a black hole, maybe the information doesn't fall in to be lost, but gets imprinted on the event horizon somehow.
Okay, cool idea, but maybe a bit vague. Did it get more concrete?
It did, big time. In 1997, Juan Meldacena came up with the ADA-CFT correspondence, anti-de Sitter space conformal field theory.
Sounds complex.
It is, but the core idea is a precise mathematical link, a duality between two very different theories. One is a theory of quantum gravity, like string theory, living in a specific kind of curved space-time called anti-de Sitter space, the bulk. The other is a normal quantum field theory, without gravity, living on the boundary of that space.
And they're equivalent.
In a very deep way, yes. What happens in the bulk has an exact mirror image on the boundary, and vice versa. A black hole in the bulk corresponds precisely to something like a hot, soupy plasma on the boundary.
So how did that help with the information paradox?
With the boundary theory, the CFT is a standard quantum theory. It must obey unitarity. Information is always conserved there.
Ah, so if the boundary theory conserves information...
And it's exactly equivalent to the gravity theory in the bulk.
Then the black hole evaporation in the bulk must also conserve information when viewed through this duality.
Bingo. The information falling into the ADS black hole isn't lost. It gets encoded holographically in the boundary theory.
That sounds huge, like proof that information isn't lost, at least in this model universe.
It was absolutely a game changer. The first rigorous framework showing information could be preserved. It was so convincing, Stephen Hawking actually conceded his famous bet in 2005 because of it. He admitted information probably wasn't lost. But, and it's a big but, ADS space is a specific mathematical setup. It's got this negative curvature. It's not expanding like our universe. It's a toy model.
So it showed it could work in principle, but not necessarily how it works in our universe.
Exactly. It proved unitarity can win, but the mechanism in our cosmos was still a mystery. But it fundamentally shifted thinking maybe space-time itself isn't the fundamental thing. Maybe it emerges from quantum entanglement, like a hologram.
Okay, so information is saved somehow, but how? That question just led to more weird ideas, didn't it? Like the firewall.
Yeah, things got even stranger.
Yeah.
In 2012, you had the AMPS paper, Almeri, Marov, Bolchinski, Sully. They pointed out a massive inconsistency if you try to make everything work for an old black hole, one that's past that page time. They showed you hit a contradiction between three basic ideas. One, unitarity has to hold. Two, Einstein's equivalence principle holds, meaning falling into a black hole should be uneventful, no drama at the horizon. Three, local physics works as expected, effective field theory.
You couldn't have all three.
Nope, it came down to this quantum rule, monogamy of entanglement. Basically, one particle can't be fully entangled with two separate things simultaneously. But for an old black hole, it looked like an outgoing Hawking particle needed to be entangled both with the radiation that left earlier and with its partner particle falling inside. Quantum mechanics forbids that. Something had to give.
So what did AMPS propose breaking?
They made a radical choice. Ditch the equivalence principle at the horizon, forget no drama. They suggested the entanglement gets violently broken right at the horizon, creating an incredibly hot, high-energy barrier, a firewall. Anything trying to cross would be instantly fried.
Ouch. That really messes with the smooth picture of falling into a black hole.
Totally. It was a shocking idea, replacing this smooth gateway with a wall of fire.
But there were other ideas too, right? Like fuzzballs.
Yes, from string theory came the fuzzball conjecture, mainly pushed by Samir Mathur. This idea says a black hole isn't empty space with a singularity and a sharp horizon. Instead, it's a quantum object, a fuzzball, basically a tangled mess of strings and brains about the size of the would-be horizon, but without a true horizon or singularity inside.
So how does that help?
Well, if there's no classical horizon, the whole firewall problem kind of evaporates. Information doesn't fall behind a point of no return. It gets absorbed into this complex fuzzball state. Then the fuzzball radiates thermally from its surface, but because the information is encoded in its structure, the radiation carries it away gradually. Information preserved, no firewall needed.
Okay, firewalls are fuzzballs. Then came another really wild one, EPR, wormholes and entanglement being the same thing.
Yeah, Maldacena and Susskind again in 2013. EPR. Einstein-Rosen bridges, wormholes, are equivalent to Einstein-Podolsky-Rosen pairs, entangled particles.
So entanglement is geometry.
In a sense, yes. The idea is that maybe the inside of the black hole isn't separate from the radiation outside. They're connected through these microscopic wormholes, manifestations of entanglement. This neatly dodges the firewall problem, too. The outgoing particle can be connected to both the earlier radiation and its infalling partner because they're all part of this wormhole-connected system. It preserves the no-drama experience.
That's really profound. Space-time itself being sewn together by entanglement.
It's a mind-bending picture suggesting geometry emerges from these quantum connections.
Were there other, less prominent ideas floating around too?
Oh yeah, people considered things like remnants, tiny, stable leftovers holding all the information.
Yeah.
But those had issues, like potentially needing infinite types, or baby universes splitting off, also problematic. More recently, Hawking, Perry, and Strominger proposed soft hair, very subtle, low-energy quantum fields at the horizon that could store information without violating the no-hair theorem too badly and then leak out with radiation. Another possible mechanism.
So, after all these ideas debating firewalls, fuzzballs, wormholes, then came 2019 and a huge shift. They actually calculated the page curve.
Monumental breakthrough, yes. Two groups, Pennington's group and the Almhiri, Engelhardt, Marolf, Maxfield group, independently managed to derive the page curve using semi-classical gravity, basically, general relativity plus some quantum field theory effects.
How on earth did they do that without a full quantum gravity theory?
They used a clever mathematical tool called the replica trick. It involves calculating things by imagining multiple identical copies or replicas of the black hole system. When they did this calculation using gravitational path integrals, they found they had to include contributions from new space-time geometries, replica wormholes. These are like tunnels connecting the different replicas.
Wormholes connecting copies of the universe.
Mathematically, yes. And these wormholes effectively allow information to be exchanged between the replicas in the calculation.
And this led to the island idea.
Exactly. These calculations produced a new formula for calculating the entropy of the radiation, often called the island formula, or the quantum extremal surface formula. It modifies Hawking's original calculation by saying, sometimes you need to include the contribution from a region inside the black hole called the island.
How does the island fix things?
Well, early on, when the black hole is young, the calculation shows there's no island needed. The entropy just goes up, like Hawking found. Problematic. But late in the evaporation after the page time, the calculation shows a non-zero island region deep inside the black hole becomes important. Including the contribution from this island makes the calculated entropy of the radiation go down.
It reproduces the page curve.
Perfectly. It showed, mathematically, how the information could get out, statistically speaking, and keep unitarity happy. The interpretation is pretty wild. It means that late in the game, some degrees of freedom deep inside the black hole of the island are somehow encoded in the radiation that's far away. The replica wormholes are the mathematical signposts for this deep connection. It fits beautifully with holography and EPR. The inside is represented by the outside.
But you said statistically. Does it tell us exactly how a specific bit of information gets out? Like if I threw my diary in, how does page 3 get encoded in the radiation?
That's the crucial subtlety. No, the calculations are amazing. They get the page curve right, confirming unitarity overall. But they don't give us a local step-by-step movie of that diary page escaping. It's a non-perturbative statistical result. It tells us the information is there in the radiation, but not the precise mechanism for its transfer. So the big picture seems resolved, but the details, especially what someone falling in actually experiences, are still very much debated.
Wow. So this whole journey, this paradox, it really became like a guidepost for quantum gravity, didn't it?
Absolutely. It's transformed from just a puzzle into maybe the most important clue we have. It forced us to put information front and center. It strongly suggests space-time geometry isn't fundamental, but emerges from entanglement. Holography, EPR, these aren't just fringe ideas anymore. And it showed semi-classical gravity is surprisingly powerful.
Is there any hope of actually seeing any effects of this experimentally?
It's incredibly tough. These are quantum gravity effects. But people are looking. One idea is gravitational wave echoes. If the horizon isn't perfectly smooth, maybe more like a fuzzball or has some structure near it, then when two black holes merge, the gravitational waves might sort of bounce off, creating faint, repeating echoes after the main signal.
And LIGO and others are looking for those.
They are. It's a long shot, but they're looking. Other ideas involve searching for tiny deviations from GR and cosmology, or maybe even future high-energy experiments. It's all pretty speculative right now, though.
So where do we stand now? Is the paradox solved?
The general feeling, the consensus, is largely yes. The original paradox, the apparent violation of unitarity, is considered resolved. Black hole evaporation is unitary. Information is preserved.
Phew. Unitarity is safe.
It seems so. But like any good scientific resolution, it's opened up even deeper questions.
Such as?
Well, the big ones are, what is the explicit mechanism? How does that information actually get from the islands to the radiation, step by step? Second, what does someone falling in really see? Is it smooth sailing or EPR style or something else? The firewall debate isn't completely dead. And third, how do all these amazing insights from ADS-CFT and replica wormholes, often derived in simplified toy universes, translate to our messy, expanding universe?
It sounds like the paradox forced us to realize space-time might be the issue.
I think that's fair to say. The problem pointed towards space-time, and the resolution points towards quantum entanglement being the weaver of space-time. It suggests reality is far stranger, far more interconnected and non-local than we ever thought.
So you've just taken this deep dive with us into one of the biggest mysteries in physics. You've seen how chasing down one bit of information near a black hole is actually reshaping how we think about the entire universe.
And maybe a final thought to leave you with. Considering this whole journey, if space-time really does emerge from quantum entanglement, what does that truly mean for reality? Does it go beyond our usual ideas of place and separation? Could the universe, at its deepest level, be like some vast quantum computer constantly processing information?
Definitely something to mull over. Thanks for joining us on the deep dive. Keep looking up, keep asking questions.